All right, let's get started. Okay, so you all have a present for me today, right? I'm collecting these here. So I have homework number 2, a big stack of them right here. I've got the sign-in sheet started, working its way around. Okay, so homework number 3, ACI beam requirements, that's due Monday. Again, that's a really short assignment. It's only two problems, but it's really just meant to make sure that everybody's okay with computing strains and computing ACI minimum requirements for steel, computing phi values, and all of that. And I think actually a separate exercise on that, a short one, but a separate exercise on that will make your life a lot easier when you do homework 4, which is a full-blown design homework. Okay? Any questions so far? How did the triangular problem go?
It's turned in.
It's turned in.
You tell us whenever you get it back. Yeah, where's the solution? Right.
You want to see the solution?
Yeah.
Okay. So now that we have revealed the solution for all the homework, we can get back to YouTube. Okay. So today what we're going to do is we're going to continue on with our design example, and I want to knock this out start to finish. We're going to follow the procedures that are listed in the slides. We're also going to, I've got a spreadsheet that I created that I'm going to show you all later where it shows just how sensitive some of these parameters are to capacity, and I think you're going to be surprised when you look at the analysis. So let's just sort of recap and make sure everybody's on the same page. So we're designing a 22-foot long beam. It's going to resist a dead load of 1 kip per foot and a live load of 2 kips per foot. Now the dead load is in addition to the beam self-weight. So the total dead load on the beam is however much the beam weighs itself, and then an additional 1 kip per foot. And if you remember, I threw the term superimposed at you. So if you ever hear the term or read the term superimposed, a superimposed load is on top of the beam self-weight. So just make sure you're aware of that. The 2 kips per foot dead load is also already reduced, so we don't have to worry about live load reduction or anything like that. Now we're going to use 4 KSI concrete, 60 KSI steel, normal weight concrete, so we'll use 150 pounds per cubic foot, and we're going to use an approximate D over B ratio of 1.5, and you'll see how that gets employed here in a little bit. And again, if you're curious how sensitive beam design is to some of these parameters, you're going to see this spreadsheet that I created here in a little bit, and I think you'll find it's kind of nifty. Another thing I'll bring up today, definitely, if you remember this beam design aid where we've got the areas and the minimum web widths, if you haven't already broken that out, I'd break that out right now because we are going to use that very soon. Okay, so here's example 6. So I started off listing some of the basic parameters of the design, and then we started going into our step-by-step process. Now step 1 is to compute the factored moments on the beam. So step 1 is a little hefty because it involves structural analysis. Okay? Now I want everybody to pay attention to this because this is kind of important. Okay? This beam is simply supported and it has a uniformly distributed load. You're going to have homework problems that have different loadings. So for instance, you're going to have problems on your homework that's a simply supported beam, and let's say it has a point load right in the middle. If you try and take that point load and collapse it into a distributed load, I'm going to do this to you because that's not what you do. Okay? The moment diagram from a point load is different than the moment diagram from a distributed load. So pay attention to the words I'm saying. If you do not have a simply supported beam with a uniformly distributed load, this is wrong. Okay? You do not use WL squared over 8. You can for the dead loads or something like that, but not for the live loads. Again, you got to use your thinking cap and make sure that you're analyzing the structure appropriately. So just make sure you're aware of that. Okay? Now, so we're going into step 1. We're determining factored moments. One of the things that we do not know is the beam self-weight because we haven't designed the beam. So we used ACI requirements to give us some guidance on how to guess how much the beam weighs. Now, in all honesty, this is probably an underestimate. We're probably missing the bar. In other words, We assume that the beam weighs about 150 pounds per foot. It's probably heavier, but it's not going to be that big of a deal because, how much does this number really affect the factored load? It affects it, but not too much, so it shouldn't be that big of a deal. Now, factor our loads, 1.2 dead plus 1.6 live. Note that I have factored both the self-weight and the dead load together, and then WL squared over 8 to get 276.5 foot kits. So that is the factored moment. That is how much moment we are putting on the beam. So this is our target. The beam has to have a FMN of either this or higher. Does that make sense? Okay, so that's step one. Step two, really easy. Now that we've got our MU, we compute the required MN. So this is a required capacity of the section. This is how much moment we need our beam to be able to resist, minus our safety factor. Now our resistance factor, our safety factor, we don't know what that is either because that's dependent upon the strain in the steel. A safe assumption is to assume that that's 0.9. So all these assumptions, we're going to go back and check later. It's just something to be aware of. So far, so good? Okay, so let's go ahead and keep on trucking. I'm going to move on to the next panel. And so help me out. What's step 3? Say it again. So, row. We compute row. All right. No, that's fine. That's fine. So we're going to compute row design. Now, if you remember, rho is a reinforcement ratio. It's a percentage of how much steel we should put in the beam versus how much concrete we should put in the beam. Now, let me pull up the spread or the PowerPoint for a second. There's a couple different ways we can go about that. So this is a more refined equation for rho, and this would be the equation that we would use for rho if we were trying to hit a target strain in our steel, like design it so that the strain in the steel is 0.005 or something like that. So we would just plug in that strain value and see what our design value is. That's one way of going about it. A simpler way of going about it is to just use this value, this rho design value. And unless otherwise noted, I would go with this. It's simple, it's straightforward, and it works pretty well. So our rho value for design is going to be 0.18 FC prime over Fy, which is 0.18 times 4 KSI over 60 KSI. What does that come out to be? 0.012. Do I have a second on that? Okay, all right. So basically what this is saying is that for our beam, about 1.2% of that beam should be steel when it's all said and done. Now I say about because this is just a value at the beginning that we're going to use for design purposes. So just take that in mind. Keep that in mind. Okay. So far so good? Okay, now what is our step 4? What are we computing in step 4? BD squared. Compute required BD squared. Now, so what we're doing in this equation is based on the assumptions that we've made thus far. We're now going to compute essentially about how big this beam should be. So BD squared is sort of a measure of how big the beam ought to be. So BD squared, and I'll say BD squared required, is computed as follows. So we're going to take MN required divided by Fy times the following. So we got a big fraction here. So on the bottom, we've got rho design, and we've got 1.7 FC prime minus rho design times Fy. And then we've got 1.7 FC prime. Remember, all this equation comes from, actually I'm going to write this down here. All this comes from is basically taking our nominal moment capacity expression, subbing in our expression for rho, and then doing a bunch of algebra and factoring out all of the terms related to B and D. So again, this is basically just an expression that we can use for design purposes. So let's plug and chug. So help me out with a couple things. What is MN required? Inch kips. There we go. I like that. The inch kip. Make sure you put your units down. Okay, what's FY? Now, 60, okay, so he said 60,000 PSI. Would it make sense to put 60,000 or 60? Because we've got inches and kips, so let's make sure that we're being consistent. Okay? That's what I put. That's what I'm saying. Like, you don't put 60,000, put 60. So, okay. All right, I'm drawing that out pretty far. So let's see. We've got 0.012 times 1.7 times 4 KSI minus 0.012 times 60 KSI. Okay, and 1.7 times 4 KSI. So I'm going to give you a second on this one. This equation's a little verbose, but everybody in this room, you really ought to go through this to make sure everybody's getting the right answer. This is one of those things where I really am going to need a second because it's long and there's a chance you all get different answers. You got a calc error in there. So 57, 26.5, something about like that? 0.3, okay. That's close enough. And say it again? Inches cubed. Everything's in kips and everything's in inches. What are we solving for? We're solving for BD squared, inches times inches squared, so it's going to come out in inches cubed. How are we doing? So rounding. So it's not. You're going to see how in a very quick second it's really not going to matter because ultimately what we're going to do is we're going to use this to determine beam dimensions, or we're going to round up anyways. So make sure you've got your parentheses where they need to go. If you're getting negative answers or wonky results, you're probably missing some parentheses or something like that. My advice would be if you're getting errors there, do the denominator first and then do this times that divided by that times whatever your denominator is. So far so good? So yeah, this is just something, just, grunt that out. Okay. 5. Okay. So step 5, what we're going to do in step 5 is we're going to compute required beam dimensions. Okay, and let me show you how I'm going to do that. What was our assumed D over B ratio? 1.5. So in other words, the depth is going to equal about 1.5 of the width. Everybody okay with that? Sound good? So help me out. What is D squared going to be? What is that quantity squared? So 2.25 B squared. So what is BD squared? 2.25 B cubed. Fair point? So could we say this? Could we say therefore 2.25 B cubed, and we'll call it B required, cubed, has got to be 5726.3 cubic inches. Could we say that? Right? Because, I mean, that's what we've got here. We've got BD squared equals that, you know. If A equals B and B equals C, then A equals C, right? Yes?
Where did we get started with B equals 1.5?
That was one of the assumptions in the problem that, hold on. That was right here. We're going to assume an approximate D over B ratio of 1.5. That's a good question. And typically, you're going to want your D over B ratios to be somewhere between like 1.5 and like 2.5, something like that. You don't want a D over B ratio of like 8 unless you've got some seriously high moments and shears. And you're also not going to want a D over B ratio of like, you know, 1/8 unless you're dealing with something like a slab. But we design slabs way differently anyway, so that's not even really an appropriate comparison. So I've got this. How would I design for, like, how do I solve for B? So I'd say required is 5726.3 inches cubed. I take that and I divide it by 2.25, and then take it and raise it to the 1/3. Say it again. 13.65 inches. Do I have a second on that? Something like that. Oh, okay, all right. So here's what I'm getting at. You're offered a little bit of like flexibility on your rounding, because what are we ultimately going to use for the width of this beam? 14 inches. We're not going to spec a beam out that's 13.65 inches. We're just going to say 14. Okay. Everybody good so far? Any questions? Okay. All right. Can I go ahead and move on to the next panel? Is everybody good? Okay. All right. So, continued. So step 6 is basically to proportion the beam. Okay, so this is what I propose that we use for this beam. So let's use the following. Let's use B equals 14 inches. Okay, if B equals 14 inches, let's use D equals 1.5 of that. And what is 1.5 of 14 inches? Nope. 21. All right. So, all right. So there's B and D, but in order to verify our self-weight assumption, we are going to need a height of the beam. What do you think the height of the beam is going to be? D plus 3 inches. So we'll say D plus 3 inches, and we'll say 24. So far, so good? So right now, we've got a beam. We know that that is 14 inches. We know that this is 21 inches. And we know we've got some steel in here. We're just not sure what it is right now. And we know that this, give me one sec, we know that this is 24 inches. So the only thing left to do is to worry about the steel, and I'm going to handle that here in a second. Yes, sir? That's a good question. Okay, so question was where the 3 inches came from, and basically it's coming from cover requirements. So this isn't the right image, but it's close enough. So you at the very least need 1.5 inches of cover. So if you take 1.5 inches of cover, take your stirrup, and then take your bar diameter, which we're not sure of yet right now, you know, that you're probably looking at something like 2, 2.5, something like that. So just to keep things simple, a very common assumption is just to say, you know what, let's just take a height of D plus 3 inches, just to cover the gamut. And that's a very common assumption within concrete design. And I have that here on step 6 where I say choose B and D values. So make sure you're selecting like to the nearest 1 inch increment. Even inch increments might even be better, you know, based on ready-made forms and whatnot. And for the height of the beam, 3 inches plus your D is pretty good way to go. That's good stuff. Yes. It's not. That's a good question. The question was, would the cover change to affect the concrete requirements? It's not the concrete that's changing. It's the application that would be changing. Cover requirements are a function of what the beam is being used for. Cover requirements for a beam, let's say, that's inside a building are going to be different than cover requirements for a beam in a bridge over brackish water. You see what I mean? Well, okay, what that issue is going to be is more about the bar spacing, the space between bars, like the space between. Hold on. Okay, that's a good question. Okay, all right. So your question is essentially related to aggregate size. Okay, you are right that that's going to affect that. Most from a design perspective, what we're really worried about when it comes to aggregate size is how far apart these bars can be. In this table right here, okay, what this table does is it assumes a maximum nominal aggregate size of 3/4 of an inch, which is really common for internal beam and column type applications, okay? And what it also assumes is that the space between bars is either your nominal max aggregate size or 1 inch, whichever governs. So that's sort of already taken into account here, which makes your life a little easier from design perspective. If you're using a different aggregate, well, then this would change. But that aggregate size is very common for building applications. So does that make sense? That's a good question, though. That's a really good question. Did everybody else get that? That was good stuff. Everybody good? All right. Okay. Let's talk about the steel. All right. So we're on step 7, which is to determine our required AS. So compute required AS. Okay. So computing our required AS, so we have AS required is rho BD. And technically at this point we could sort of compute a more accurate rho and sort of iterate this a little bit, but in most scenarios it's really not that big of a deal. We can just go with the rho that we had at the beginning. So 0.012 times 14 inches times 21 inches. 3.528. Square inches, right? Do I have a second on that? Okay. That was a simple one. Like, I was like, everybody okay? Okay. All right. So now what we're going to do is we're going to select our reinforcement. Okay. Now this is where this design aid is going to come into play. Okay. Select the reinforcement. Okay. Okay. Now, let me show you something. This top table is listing the area of bars, of multiples of bars. So for instance, if I have 3 number 6s, what's the area of 3 number 6s? 1.33 square inches. There we go. Okay. All right. So what we're going to do is we're going to use this top table to select a few patterns of reinforcement that will meet our requirements. So we have to provide at least this much steel. If not, a little more. Now I'm going to start us out, and I'm going to walk us through the first instance of this, and then you all are going to help me as we go along. Okay. Now, and you'll see how my logic and how I'm going about this pretty soon. So I'm going to draw a little table. So bar size. Okay, and like I said, I'm going to start us out. Okay, and I'm going to go ahead and just start us out. I'm going to walk before we can run. I'm going to start us out with a bar size of number 6. Okay. Now, let me ask y'all a question. Okay. If I was using number 6s, okay, number 6s. If I was using number 6s, how many number 6s would I need to use to meet this requirement? 8. Okay. Now I know some of you are like, oh, let's go up one more. Remember, we took our beam dimension. We've already rounded it up some, so there's already some conservatism. So there's a point when just use the 3.53. So go ahead, go with the 8. So 8 bars. Okay, and now let me show you what I'm writing here. I'm writing 8 bars, and we selected that because that's an area of steel of 3.53 square inches. Sound good? Okay. Now, let me ask you a question. Okay. Now I want you to look at the bottom table. Okay. In order to use, now we're going to assume a number 3 stirrup for this beam, and unless otherwise noted, always assume a number 3 stirrup. That'll make more sense later on down the line when we look at shear, but for now, always assume a number 3 stirrup. So if I got number 3 stirrups, okay, number 3 stirrups, all right, and I have number 6 bars, and I have 8 of them, how wide does this beam need to be in order to fit those bars? 17.5 inches. So the minimum width is 17.5 inches. What does that tell you? This isn't a good option, so I'm going to say no good. Now we could arrange this in like 2 layers, and we could play with that a little bit. But right now, I want to get a design that we can ultimately tweak, that we can play around with. So this beam would not make sense because our beam is only 14 inches wide. We can't fit 8 number 6s in that web. We don't have enough room. So that's sort of what I'm doing here. So let's go on. Let's keep going. And I know y'all are going to ask, like, why'd you start with a number 6? You'll see why here in a second. Okay. Well, let's try number 7. Okay, a number 7. All right. How many number 7s would satisfy this requirement? 6. Okay, so 6 number 7s. And you selected 6 number 7s because it has an area of steel of 3.61 inches squared. Is that a viable option? So number 7s, this is 14.6. I don't think that's good, right? Is everybody following along with me? That's no good. How are we doing? Yes.
How much do we have to have on each side of the web?
What? Well, okay, so what we're talking about, remember, like if I've got a beam that looks like that, the web width is that dimension. But since we're dealing with a beam that's just rectangular, we're just talking about the width of the beam. That's all we're talking about. What I'm saying here is, like, 6 number 7s would be a viable option from a structural standpoint, but from a reality standpoint, we can't fit 6 number 7s inside this beam. No, I can understand that.
What's the stirrup again?
Okay, the stirrup is this. The stirrup is this little U-shaped thing inside the middle of the beam. We use stirrups to tie the rebar together, but also to resist shear. We're going to do shear later. So for now, like, unless otherwise noted, just assume number 3. Like, if you're using number 4 stirrups, you got some shear going on. You got some serious shear. Not saying that isn't something we'll consider down the line, but number 3s are very common.
Like a holder for the rebar.
Yeah. For now, that's basically all you need to assume it as. It's just tying all the rebar together. All right. So everybody's sort of seeing what I'm doing here? Okay. All right. All right. So number 8s. Okay. 5 of them. All right. So how much steel is that? Okay. Now, what's the minimum beam width for 5 number 8s?
13.25.
13.3. So this is a viable option, right?
Don't really have much cover on this.
Well, no, we're meeting all our cover requirements. That's incorporating cover.
On the sides.
Yes. So it's one of those things where it's like everybody's like, oh, well, we ought to round it up. So no, we've already taken all that into account. So no, like once you meet the requirement, like there's got to be a point where you use it. So that's what we're doing here. So we could stop right now, okay? We could stop, but I want to carry this through a little bit because I want to see how this works out, okay? Let's look at number 9s, okay? And you're going to see where I'm going with this here in a second. How many number 9s would you pick? 4. And why'd you pick that? 4.00 square inches. Is this a viable option? Why? And what is that? Somebody else. There we go. 12.0 inches. So this is okay. Now, let me ask you this. If these are our only 2 options, which would you go with? Number 9s? What do you think if you're buying steel by the pound, which is cheaper? There you go. Less area of steel. Okay. Now there is a little bit of a question, like, well, that's less pounds per steel, but this is more bars, and that's more labor. So that's a loaded discussion. For our purposes, we're just going to go with minimum area of steel. But you could take this and you could carry it on one step further. You could even go any further and say, well, maybe my rebar supplier doesn't have any number 8s in stock or what have you. You could drive yourself crazy with it. So that's what senior design's all about. So right now we're just trying to deal with something that makes sense. So for our purposes in this class, minimum area of steel is going to govern. That is not always the most economical option in the real world. We got to have a metric in this class. Okay, let's look at number 10s. How many number 10s would work? All right. Why is that? What's the area of steel? Somebody else. 3.82. Okay. Now, what's our minimum beam width for that? 10.3. So that's okay, right? Sound good? Okay, all right. So let's make a couple observations. Number 1, if I were to go to like number 11s, number 14s, number 18s, do you think my minimum beam width requirement would be met? Yeah, because there's a trend that like the bigger bar size that you're using, the less of those bars that you need, okay? So that's one of the reasons why I'm sort of stopping here. That's one reason I'm stopping here. That's another reason why I didn't look at number 5s, number 4s, number 3s, because think about it like this. How many number 3s would you need to meet this requirement? Like 30 or 40? Do you think you could fit those in 14 inches of beam width? No, there's no point. So you can see why I was being a little trying to be feasible with it. That wouldn't be a viable option. Okay, so that's why I started at number 6 to try and start with something that makes sense. Now let's just conduct an academic exercise. Of these 3, which one would you pick? The number 10s. Okay, the number 10s, 3.82. Now let's keep that number in our head. Number 11s, what would our area be? Number 11s, what would the area be? 4.69. Is that economical compared to this? No. What about number 14s? 4.5. Is that economical compared to this? No. What about number 18s? It's not economical compared to this, right? So I propose that the most economical solution is to use 3 number 10s. There's our beam design right there. So therefore, trial beam here's our beam. This is 14 inches. This is 21 inches. This is 24 inches. Three number 10s. Bam. What do you think? Now you have a real beam that we can begin to assess. But we're not done with this problem, okay? Because there's something that we got to go back and check. We got to go back and check those assumptions, right? We assumed the beam self-weight, okay? We assumed what phi value is, what our phi value is. We don't know that that's right. We arrived at this beam based on guesses. We have to check those guesses. So step 9 is to analyze the beam. Okay? Does that make sense? Any questions? All right. Can I move on to the next panel? Okay, so step 9. Analyze trial section. And I'm calling it a trial because it is very possible that this beam doesn't work. Design's iterative. I mean, it's just the nature of the process. So it's just something that you gotta deal with. So I'm gonna walk you through this. The first step is to compute the beam self-weight again, because we guessed that before. So how do you compute beam self-weight? You take gamma, what do you multiply it by? The area, BH. So that's 0.15 kips per cubic foot times 14 inches times 24 inches. Notice, I'm using the real values. We now have a beam we can analyze. Got to convert our units. What do we get? I have a second on that? 0.350 kips per foot. What did we get initially? What did we get before when we did this in step 1? So the beam that we got is heavier than we assumed. See, this is one of those things, like, it's good that we're going back and checking this. Everybody with me on that? All right, so W sub U is 1.2 W naught plus WD plus 1.6 WL. So that's 1.2 times 0.35 kip per foot plus 1 kip per foot. Remember, that was the superimposed dead load. Plus 1.6 times 2 kip per foot. What are we getting there? $4.82. Do I have a second on that? Yeah. Okay. Okay. And our MU is WUL squared over 8, which is 4.82 kips per foot. How long was this beam, by the way? 22 feet. And what's that? Actually, here, I'll move that up. Let me move that over here. So, MU. So 291.6, we'll say, foot kips. So far, so good? Okay, now that's the loads. Let's look at the resistance. So I'm going to walk you through the resistance. First thing, A equals ASFY over 0.85 FC prime B, right? So 3.82 square inches times 60 KSI. Am I going too fast, or is everybody with me on this? Times 14 inches. Again, use your real dimensions, not your fake dimensions, or your assumed dimensions, is what I mean. Like, don't use the beam in. Like, use the real width. What does that come out to be? Say it again. 4.82 inches, right? Okay. So MN is ASFY D minus A over 2, which is 3.82 square inches, 60 KSI, times, what was D? 21 inches minus 4.82 over 2. And what does that come out to be? $4260.8. What are the units? Inch kips. So why don't we go ahead and convert that to foot kips by dividing by 12? 355.1. Everybody good so far? Okay. That's nominal moment. We need a design moment capacity. We need to take that and adjust it by our phi value, our resistance factor. What is phi? It depends on what? How do you determine what phi is? What do you have to compute? You have to compute the strain in the steel. Remember that? So C is A over beta 1, which is 4.82 inches divided by what's beta 1? No. Beta 1 changes dependent upon your FC prime. So it's in the last lecture. Yep. What do you got? What do we got here? Say it again. Do I have a second on that? Okay. So the next thing we've got to compute is our strain in our steel. How do we do that? .003 times, there we go, similar triangles. So 0.003, 21 inches minus 5.67 inches divided by 5.67 inches. What does that come out to be? .0081. Do I got a second on that? Okay, so we can make two observations. It's bigger than .004. So that's good. It meets the ACI minimum requirement. What does that also tell us? It's bigger than .005, so phi is 0.9. So epsilon sub t is greater than or equal to 0.004. So that's okay. That's good. And epsilon sub t is greater than or equal to 0.005. And that tells us that phi is 0.9. So when we look at our assumptions, our first assumption on the beam weight, we underestimated the beam weight, but we were right on the phi value. So help me out. Phi mn is 0.9 times, what's MN? 355.1 foot kips. What does that come out to be?
319.59.
Say it again.
319.59.
319, so here, so 319.6. All right, so do I have a second on that? Everybody with me so far? I want you to pay attention up here. I want to see something. I want to look at these two red underlined numbers. This number right here on the bottom, phi mn, that is how much the beam can withstand with all of our safety factors applied. And I propose that this beam can hold up about 319.6 foot kips. This up here is how much we're putting on it. We're putting on it 291.6 foot kips with all our safety factors applied. So is this beam adequate? It's good, right? Now, do you want to grade this? You want to see how efficient it is? Watch this. Okay, so first off, all right, let me do a little sort of thought bubble over here on the side. So first off, we agree that phi mn is greater than or equal to mu, so we're okay. That's good, right? There is a term in structural engineering called, and in bridge engineering we call the term a performance ratio. Sometimes in building engineering it's referred to as an efficiency. To calculate the efficiency, what we do is we do this, okay? We take, and I know we're getting close to ending, but this will be a perfect place to end. So we're taking mu and we're dividing it by phi mn. So that's 291.6 foot kips divided by 319.6 foot kips. What does that come out to be? 0.91. Is that what you said? I got a second on that? So how about this? Would that be a 91%? Okay. So here's the thing. This is a good design, okay? It's a good design because it got an A. Got a 91%. And here's a rule of thumb. If your design has an efficiency of 90 or above, you're good. Don't redesign anything, okay? Now, two questions. What if your efficiency is like 60%? You got to redesign it. And what does that mean? Tell me what 60% efficiency means. The beam's too big. It's too conservative. There's too much going on. Now, so if you get an efficiency of 60%, you got to redesign. And that usually means trimming something up, making it shallower, using less reinforcement. Now, what if your efficiency is like 120%? What does that mean? It failed, right? It's failed. It's like the Price is Right. It's like get closest to 100% without going over, right? It's a lot like that. So as long as this number is lower than 1 or lower than 100%, you're good. It can be right at 100%, but analytically that's very rare. So in the 90s, that's a good design. Move on. Yes. Hold on. One quick question and we're good.
So let's say I do one full iteration of this where I can get my efficiency factor and I do this in Excel. Can I go back and say, okay, let's make this 1 by changing B and automatically go ahead and...
We're going to talk about that on Friday, and we're going to talk about what parameters will actually affect it the most. You'll be surprised if you double FC prime, doesn't change it that much. You'd be surprised. FC prime actually isn't that big of a deal. So that's all I got, guys. I will see you all on Friday.